Hello and welcome back to the Renewable Energy Technology course. I am Miro and this is the second lecture on wind turbines and wind power. We will focus here on the mechanical component. Generally, this is exactly the topic of the lecture and nothing else. There are also other issues related to this, maintenance issues, and I will also try to put in some aspects related to small-scale wind turbines. This lecture is divided into 7 smaller sections, and we will start, of course, with the introduction and overview. Now, most of all, a wind turbine is a full-scale power plant. It contains everything from primary energy resource conversion to feeding it into the power grid. There are many aspects and many fields of engineering and not engineering involved in designing, developing, installing, running, maintaining and paying back, so to say, the wind turbine. First of all, aerodynamics, of course, mechanical engineering, electrical engineering, electronics, sensors, civil engineering, transport, logistics. Maybe sometimes you're not even able to transport the big devices and all the hardware to the field, and the cranes necessary to install it, and the human power necessary to install it, and so on and so on. Architectural issues, design, economics, project planning, everything actually plays a vital role in developing and installing and running wind turbines. Each of these fields deserves a course of its own, not just a lecture, but a full-scale course. And if you go to Denmark, you can actually have a full-scale 2 years master program on wind turbines, only on wind turbines, because you see it's quite a wide aspect of topics that needs to be discussed. We will only scratch on the surface here regarding the components in this lecture. And this is a childish representation that you can find on several places out on the internet. I believe you are far above or beyond this point. But the bottom line is that pictures like that are very easy, not only to explain to others what happens in a wind turbine, but maybe also to comprehend yourselves the secrets and the small details related to the technology. First of all, there should be a rotor, big rotor, wind rotor with blades. If the blade is pitching, it would be flipping like this. Then there should be the rotor shaft. This is the main shaft holding the rotor. It has to be supported with bearings, and it has to have, maybe not, maybe yes, a gearbox. The gearbox is transferring the torque and the rotational power to a generator of any type. The electrical generator will sit somewhere here in the nacelle. We are talking about a horizontal axis wind turbine only in these lectures. And it will be connected in some way to the grid through the tower. There is a transformer down there. The grid connection is not important for this lecture. And of course, there will be some kind of a measurement system, anemometer, and the wind vane, measuring the direction and velocity of the wind at any moment, and feeding back signals to the controller of the machine. We also need to have the yaw system. That would be the azimuth drive for the horizontal axis wind turbine, so that it's able to face the wind. All these components, let's say, or systems, need to play together in the best way. And they have to be present, regardless of how big or how small your turbine is. This is how things really look like if we take actual example. Even if this machine is a bit old, there are heaps of those still operating quite efficiently out there in the field. Maybe not the best example, but definitely one of the best pictures you can find, drawings out there in the available literature. This is the Ecotechnia machine showing the hub, very nicely colored, each of the components, the rotor shaft, the gearbox, the high-speed shaft towards the electrical generator, any kind of control, and so on, the yaw ring with the yaw motors. Very easy to see what we need to have. Braking system on the high-speed shaft, also on the low-speed rotor shaft. We don't need to talk about all of these components. We will focus on the most important ones and the most vital ones for the operation of the machine, which also happen to be the most expensive ones, of course. Another nice photo from the assembly line of GE Wind Energy 1.5 megawatt machines, actually in Germany. Again, very easy to see what's going on and how things are fitted in. So this is the canopy, the entire nacelle. It's a 1.5 megawatt machine, not really very big nowadays, but these are still one of those most desired turbines that are purchased and installed. We do have 6 megawatt machines today. Nobody is buying them. People are buying those turbines still. And heaps of those are out there operating. So if you need to maintain something, it might very well be this kind of turbine. It's not much to see. The blades are missing. The whole hub is missing. But, well, you can imagine the dimensions that you work with when it's a 1.5 megawatt output. And, of course, the nacelle is made big enough so you can actually get in and do some maintenance or repair out there in the field. The early types of nacelle arrangements, very depictive, even if not so important to talk about those right now. Well, it's probably important to mention that many of these old and funky machines are actually very good performing, and some of them are older than 20 years now. Typical types of how you fit the major components inside the nacelle. It doesn't matter actually what the choice is. Any kind of arrangement may work fine. It is a matter of choice in terms of what components you work with, how you want everything to be built, how well you want to balance the rotor, and ultimately it comes down to costs. Or if you would be a wind turbine manufacturer, it comes down to some kind of experience that you already have, maybe with another machine. And that's how in the early days people chose what kind of arrangement they would use. Some examples, very good examples. I have personally seen this machine. It's built in '94, installed in '95. It's still operating. A good example of a super short, compact nacelle. This is the generator, the gearbox casing. It holds in itself, actually, inbuilt flanges where the rotor shaft, the main wind rotor shaft, is actually a console hanging on the main input shaft for the gearbox. The generator, the high-speed shaft, is right here. The generator is simply also hanging flanged to the gearbox. Super compact. This is how it looks in real life. You don't need big nacelle. This is one example for a Micon-produced machine. Both these names do not exist anymore, but there are the machines still operating out there. In usually below 1 megawatt range. This is the other extreme, again a good example. Now exactly this one is a 1 megawatt machine. The name doesn't, or the make doesn't exist anymore either, but it actually is a part of Siemens now, so the factory is there. It represents another approach, the very long extended nacelle. Again, doesn't matter how you fit things inside. Here the choice simply is to have a long, well-balanced, low-speed rotor, the rotor shaft, properly supported by 2 bearings. Behind it, the gearbox, the high-speed shaft, the generator, also supported properly, not hanging, not flanged directly to the gearbox. So you have space for couplings, brakes, and so on and so on. And of course, measurement and control systems. We don't need to stop on these drawings. You're free to look at them in details when you have the slides later on. Contemporary nacelle arrangements for the large multi-megawatt machines that we usually use these days and install now as new can be divided in 4 basic types. You will talk about those types with another lecturer, and this is a drawing borrowed by Thomas Ackermann, which is your other lecturer for this course. I will simply mention the most important points here. The four main types are divided indeed not in terms of mechanical engineering, but in terms of electrical components and connection or type of connection to the electrical grid. The simple Danish concept that we talked about now, both examples that we showed before, actually belong to the simplest, most robust, the so-called Danish concept, the first generation wind turbines. They were the prevailing commercial machines approximately 20-15 years back in time. There is one of the most famous manufacturers, that would be Vestas, also Danish and still Danish, which from the very early days actually preferred a different arrangement. Also, slightly more modern machines may choose to work with doubly fed induction generators. And the last option is the full converter. Short description of all of these options. The Danish concept, stall controlled, very robust, very simple. Best choice in the old days, usually using off-the-shelf induction generator. Well, no components are off-the-shelf in wind turbines. All of them are tailor-made. But the Danish concept, or the stall-controlled machine, is typically using the simplest generator you can imagine. That would be the squirrel cage induction generator. The variable resistance concept is actually a pitch-controlled Danish type preferred by Vestas, where pitch control is used for optimum performance, but then you would need actually to act somehow on the generator to smoothen out the performance and to wipe out as much as possible the induced vibrations, which directly are transferred to the output power, decreasing the quality of the output power. The stochastical variations and harmonics in the electrical output are not desired, especially when we go to big machines. So the variable resistance is actually using a wired rotor induction generator and acting on the rotor currents to smoothen out the performance. Next option, the double-fed induction generator, allowing for a wider window of variable rotor operation, a larger window of optimum tip-speed ratios. Also allowing for island mode operation, grid independent, because the Danish concept actually is not able to do that. If the grid is not there, your machine cannot operate. The doubly fed induction generator is a wired rotor induction, that is, generator, where only the rotor current is conditioned in a frequency converter system. So you actually can act on the generator and control it very easily, not handling the entire power output. The starter is somehow almost directly connected to the electrical grid. And the full converter is now easy to guess the other extreme, where any kind of generator can be used. Preferably, a synchronous generator matches very nicely this concept, operating at very large window of variable speed operation for the wind rotor. Very effective, optimum design, nice performance machine, and all the power coming out from the generator at varying voltage, because of the variable operation and the synchronous generator usually used, needs to be conditioned going through a frequency converter. All the power. So it is a naturally indirect connection to the grid where all the power is handled by a frequency converter. Quick summary. Regardless of the drivetrain, the turbine will always contain the main components. There should be blades and a wind rotor as a first step of converting kinetic energy of wind into mechanical rotation. And there has to be a generator if you would produce electricity. That would be the electrical generator of any type. Whether there is a gearbox in between depends on the choice, the size of rotor and generator, of course. How the grid connection is achieved, again, depends on the choices in electrical components and on how the turbine is supposed to perform. Large modern turbines they all actually use somehow complicated electrical concepts. The mechanical arrangement is not so important anymore as it was with the early types. A wind turbine is a super complete power plant. It involves very, very different and various fields of engineering. It is impossible to say that you're actually a specialist in wind turbines, because then it means that you're a specialist in everything from aerodynamics, mechanical engineering, electrical engineering, and you get it. What is possible to be an expert of is the basic understanding, and that's actually is the focus for these lectures. Thank you.